There we go. Oh my god, and I'm tiny. Does everyone see how I'm little? Look at me! I'm moving around. I'm going on a trip. I'm walking around. Let me change it. I don't know why it's so small. It's not supposed to be that small. Okay, what's wrong with it? Okay, that was not right. It's tiny again. Yeah, like the DVD thing bouncing around the corners. There we go. Oh my gosh. Yeah. Like it goes like that. And then boing. 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 I could like spend hours doing this. So, okay, we're going to talk about distribution. So we learned about the normal distribution. Okay? And the normal distribution shows up in a lot of contexts. We found out that it shows up in the context of things like height, weight. A lot of evolutionary processes follow a normal distribution. Today I'm not in the mood to work, but I have to go to work. Oh, I'm sorry about that, BB. I know that you work a lot, so that's like unfortunate to hear. I sort of feel the same a lot of the time. How's everyone in terms of like your motivation levels? Let's drop it in the chat. How motivated are we? I want to see. Honest answers only. Low, burnt, yeah. That's sort of like how I'm feeling for sure. Minus 10.5. Don't want to go to work later either. Where do you guys work? What do you do? I'm curious. Oh, you work at a tea place? That's cool. If I show up, will I get like a teacher discount? Oh, whoa. Property manager. Oh yeah, I remember that. You were talking about like the places you were renting in like Cupertino and stuff. Ooh, working with kids with autism. That sounds like it could be hard. It sounds like it could be interesting. Trader Joe's. See, I have like the hookups everywhere apparently. Maybe I can get like cheap tea. I can get, that Trader Joe's discount. You never know. Karen can hook me up with a cheaper place. Pandan waffles. Yeah, pandan waffles are good. Isn't that like the coconut flavoring? Free Prime. If I have people who work at like Amazon. That would be hilarious. So yeah, the motivation levels are definitely low. I understand and I acknowledge that. It really sucks. Actually, okay, so my brother, he's in community college right now. And it's really hilarious because he like calls me whenever he needs help with like math courses basically. He's like, yo, bro, I need some help. So I'll like be on my computer and I'll just like randomly get like a FaceTime call from him. And it's like really hilarious. He just like, he'll call me up and he'll be like, yeah, I need help with this. He basically gets like free tutoring. And, it's not like I can like, what's it called? My brother, like just like not pick up. I'd feel really bad. Yeah, I know. It's like sort of funny. He's the connections. He's always joking like, oh man, I'm gonna like totally take your stats class. And, it's pretty funny because he's in SoCal. Oh, your mom is... Yeah, it's really great when you have the hookups with your family, because then you don't have to, like, go anywhere. You're just, like... You, like, scream out your door, and you're like, yo, I need some help with whatever. Oh, cool. Where are you from in SoCal? I grew up in Los Angeles. I grew up in between the 710 and the 210. Oh. Oh, by West Covina. That's where all the rich Asians are. Yeah, no, there's a lot of rich Chinese people. There's a lot of Filipinos in that area. Definitely. Actually, that's the one thing I really miss about Los Angeles, because, like, the food down there is just so much better than it is up here. Like, I don't know what to say about it. Like, I mean, I love a lot of things about the Bay Area, but like, let's just say the ethnic food is not as good for sure. Like the quality, the availability, like everything. Alright, so now that we've got everyone a little more, your energy levels hopefully slightly elevated, I'm going to take advantage of that and make you learn math. Okay, so let's do this. So, the geometric distribution, its context is when you are interested in figuring out how many failures you will encounter before you succeed. And so the context is you are interested in figuring out how many failures you will encounter before you succeed. Okay. So notice we're talking about how many failures. So you remember when you're talking about numerical distributions, there's two types. There's a discrete, and then there's continuous. What is the difference between discrete and continuous? If we can remember. Let's see what people remember. What is the difference between discrete and continuous? Yes! Which one is which? Yes! Yes! Awesome. Sweet. We do remember. I feel like I've done my job. This is nice. Okay. So, the normal distribution only applies to things which are measured. It is a continuous distribution. The geometric distribution is about counting how many failures you're going to have before you succeed. That is a discrete distribution. Okay, so they end up working similar but different. You have to keep this in mind. Like, you can have someone, if you're talking about heights, you can have like someone who's 5.77 feet tall. But if you're counting the number of failures, like there's only a whole number of them. Okay, so before we talk about the geometric distribution, we have to talk about something called the Bernoulli distribution. So this Bernoulli distribution is going to be a distribution which is like the basis for the geometric and other distributions. Okay, so the Bernoulli distribution is super simple. So a Bernoulli distribution looks at events, and each event only has one of two outcomes. Each outcome is either a success or the outcome is a failure. Okay, so if you're analyzing something and there's more than two outcomes, it can't be a Bernoulli distribution. It can't be a geometric distribution. So when we're dealing in the context of these problems, we are assuming that there's only two possible outcomes. It's either a success or it's a failure. There's no in between. Okay. Another requirement is that the probability of success has to be the same each time. So that means the probability of success is fixed. In other words, it has to be the same each time. And that probability, we're going to call it P. So let me give you some examples of things which are Bernoulli distributions. If you look at flipping a coin, okay, what are the two outcomes to flipping a coin? Right. You can call one of those success and you can call one of those failures. It doesn't matter which one you want to choose. You just need to choose. So you could say, I don't know, success is heads, failure is tails, and then what is the probability of success each time you flip the coin? Unchanged. Exactly. Okay. So if you look at flipping a coin, you can think of that as each time you do it as a Bernoulli distribution. There's only two outcomes, and the probability is fixed each time. It's 50%. You could do lots of other things. A die. But you have to be a little more careful with this one. Let's just say that success is rolling a 1 and a failure is everything else. So if you roll a 2, a 3, a 4, a 5, a 6, all those would be failures. But rolling the 1 is a success. Okay, so what's your probability of success each time that you roll the die? What do we think? Am I the only one with my camera on? Yes, I am. I'm alone in the universe. So if you have 6 outcomes and one of them is the winner, what is the probability of getting that one outcome as a fraction? Yeah, 16%. You got that from the 1/6. Nice. Okay, so these are all Bernoulli distributions. Okay, so this Bernoulli distribution is going to be the basis of our geometric distribution. Because the Bernoulli distribution is just saying, like, look, we care about 2 outcomes. Everything is either a success or a failure, and the probability of success is fixed. Because that ends up being the basis for what we're doing. Let me scroll down. Okay, crap. There we go. So let's look at the geometric distribution now. So the geometric distribution requires that you're dealing with a Bernoulli distribution, then plus other things. So because it's a Bernoulli distribution means that you're dealing with the 2 outcomes, success or failure. You also know that the probability is fixed each time, the stuff that we just talked about above. So the geometric distribution is used to describe how many trials it takes to observe a first success. So let me give you an example of this. So let's say that you're, does everyone know what free throws are in basketball? So let's say that, yeah, cool. So let's say that you're making free throws. And you're interested in calculating the probability. Oh, my eye itches. And I did not write probability very well. The probability that it takes 4 misses till your first success. Okay, so you have to remember that the geometric distribution is about looking at how many failures until you finally get a success. So in this case, we're saying like, okay, look, it was a miss, it was a failure. it's a failure, it's a failure, it's a failure, and then finally you get your success. Oh my god, my eye itches. Ah! Okay, so we have some notation to describe what's going on here. N is the total number of trials. So does it make sense that each time you try to take a free throw, that's a trial? So each free throw is a trial. And why is a free throw a Bernoulli distribution? Like, what makes each time you take a free throw a Bernoulli distribution? Yeah, right. It's either you make it or you don't, right? There's only the two outcomes. And then what's the other thing? So it only has the two outcomes, the success or failure. And what's the other requirement? So if you scroll up in your notes or turn the page or whatever, like, yeah, what's the other thing that needs to be true to say that you're dealing with a Bernoulli distribution? So yeah, so the fact is there's probably some like fixed probability of success that you make a free throw each time. Okay, so you're dealing with a Bernoulli distribution. That's good, and we're taking shots until we get our first success. That's what makes it a geometric distribution. Okay, so N is going to be the total number of trials. How many trials did it take before I stopped? Like, what is my N equal to in this case? Like, how many trials in total are we dealing with in this example? 5, yeah, because you took four failures, 1 success, total of 5. Okay, now for us, X is going to be the number of failures. So what's my X in this case? 4, yes. Right, because you had your 4 failures and then you got your first success for a total of 5 trials. Like, so every time you flip a coin, what's the chance of success? 50%. You need to be dealing with something like that. The probability cannot change each time you repeat the trial. So if you think, you know how like in basketball statistics, they talk about like what's your free throw percentage? That's the probability that someone makes a free throw, basically, and that's fixed. Oh, you either make it or you don't. So like, oh my god, here, we're gonna look something up. This is gonna be cool. Okay, let me share my screen. Okay, does everyone see my web browser? Do we see it? Okay, Shaquille O'Neal has a famously bad free throw percentage. If you total up all of the free throws he ever attempted in his career, what percentage did he make? 52.7. He has it's like really bad. So like the way they calculate this is they just so like that's why they have it's horrible. Look, we can even look to see how many free throws did he take in his whole career. Apparently he made 5,300 free throws, of which he only made 52% of them. Yeah, exactly. Because remember, we're frequentists. Remember, this whole idea is that probability is if you were to keep repeating something forever and ever, like what would the percentage be at the end? And the law of large numbers says, well, as the number of attempts gets really big, that percentage is going to be really close to what would happen if you did it forever. So 5,300 free throws is pretty large. It's a pretty good estimate of what his free throw probability is. That's actually why they have baseball statistics and all that. It allows you to, and baseball and basketball statistics, it actually allows you to, that's why they do the records each game. It allows you to like make predictions to figure out like how accurate people are and like what they're gonna do. So does that answer that question? In terms of like how they got it? Okay, cool. Awesome. Okay, so let's keep going forward. There's some other stuff we need to talk about. Okay, so we talk about X is the number of failures, N is the total number of trials. Okay, so I'm going to open a Wolfram. And I want to show you something. So 1 second while I open it. Okay, let me change the screen that I'm sharing. There we go. Okay, so let me adjust that. There we go. That should be easier to read now. Okay, so remember how there was the normal distribution command? Guess what command there also is? A geometric distribution command. Okay, and the normal distribution, let's just type this down. The normal distribution had two parameters. What were the parameters? The numbers that you needed to know to work with the normal distribution. Remember how I said like the parameters are the numbers that you need to know to work with it? Yeah, the mean and the standard deviation. Okay, so the geometric distribution also has parameters. And it has one parameter. You need to know the probability of success, which is P. Okay. 1 second. Okay, so we're going to do an example here. We are going to look at the geometric distribution for Shaq making a free throw. So the one number that we need to know is 0.527. Does it make sense? This comes from the fact that Shaq had a lifetime free throw average of 52.7%. Okay, so inside geometric distribution, I'm going to put P equals 0.527. Oops. Okay, and we're going to do stuff with this. Okay, so you have one, what's it called? Parameter. It's the probability of success. Okay, now just let me type this in and I'm going to explain what it is. Okay, so this is really cool. What I'm having the computer do is, here, let's type this down. We are going to have the computer simulate Shaq taking free throws. Now, because this is a geometric distribution, he keeps taking free throws until what? Like, when do you stop? Like, what does the geometric distribution look at? Yeah, so because it is a geometric distribution, the numbers below show us how many free throws Shaq took until he finally made a free throw. And actually, it's not how many free throws Shaq took, it's how many failures Shaq took until he finally made a free throw. Okay, so this is going to be a little confusing. So if you look at this, do you see how the first number is a 0? That means he had 0 failures before he succeeded. So when did he succeed? It's a little weird. If you have 0 failures before you're yeah, exactly. He made it on the first time. Good. So does that make sense though? That that's a little weird at first. Okay, so this number, the numbers that it gives you are the x's. Do you see how I put x equals random variate? That's the number of failures before he did it. Now, the 1,000 here means let's have Shaq do this 1,000 times. So the first time, he made it on the first shot because he had 0 failures. On the second time, how many shots did he take before he finally made it? Well, no. He took 1 shot, he missed. That's the 1 failure, and he made it on the second. Okay, so if you look around, like you can see, like right here, can you see like down here? You see how he took him 5 shots before he finally made it? He made it on the 6th try. You can just like look around to see like what's very common. So we're gonna look at this. Okay, so what we're going to do to this is we are going to look at the histogram of it. Actually, let's do the bar plot. Bar chart. Oh, okay, wait, that's not that. There we go. Type in the labels. Okay, there. Okay, so looking at this, it gives you an idea of the relative size of like which ones were most common. So, how many times did Shaq make it on the first try? You look right here. Actually, let me share my screen instead of doing it this way. It's like not showing up the right way. Sorry. What the hell happened to my annotate? There we go. Okay, so when I click on this, you see how the 0, does everyone see the 55 right here? Can you see that now? Is the 55 showing up? Do you see like the little box when I hover my mouse? Okay, cool. So, okay, so this right here is we're looking at x equals 0. That's the number of failures. So he made it on the first shot. How many times did he make it on the first shot? 55 times. Okay, the next one is 1 failure and then a success. So he made it on the second shot 275 times. So 275 times he made it on the second shot. 55 times he made it on the first shot. How many times did he make it on the third shot? Let's hover over it, and it's 525 times. How many times did he make it on the fourth shot? Well, you hover over it and you find out it's 102 times. Okay, so just looking at the data, how many times are you thinking is most typical for Shaq to finally make a free throw? Like, what is the most common occurrence? Yeah. So what is the most common occurrence? Typically, Shaq makes it on the third try. And this is why the geometric distribution is interesting, because if you need someone to make the free throw on the first shot, is Shaq a very good person to choose to do this? No. Yeah, right. Chances are it's going to take him 3 tries to finally make it. Like, most of the time, that is how it works. Okay, and the geometric distribution allows you to do this sort of analysis. Okay? Making sense so far? Okay, I'm going to clear that. Good, good, good. So I'm going to show you some other examples like this. Okay, we'll stop the share and we'll go back over here. So we're going to look at what happens when you change the probability of success. Okay, can someone find me like someone who's actually good at making free throws? Like, what is the best free throw? Who? Okay, cool. What's his free throw percentage? Thank you. Okay, so I'm going to type in here, plain text, Steve Nash, is that who you said? Oh, wow. 90.43%. Okay, so let's look at what happens with his. So I'm going to go in here and I'm going to replace my P equals 0.527 with P equals 0.9043. And then I'm going to do the bar chart of that. Okay, you look at his, and what do you notice? What is the most common occurrence for this dude? Like, when does this guy usually make it? Yeah, and in fact, out of the 1,000 shots that the computer simulated, like, more than 800 of them, about 900 of the shots he made on the first try. Okay, so the geometric distribution is sort of famous because it usually starts off really high and then gets really low. So if you're thinking about this as a numerical distribution, would you say that it's symmetric or would you say that it's skew? Yeah, so you should write this down. The geometric distribution is commonly skewed. Right? Like you can see with the Shaq one, it's also skewed, but it's a little more symmetric. But usually it's really high at the beginning and then gets really small. Oh shit, what's Curry's rate? Like, I'm curious. Let's just look it up. I'm going to Google it. Stephen Curry free throw. Holy crap. Where's his free throw percentage? I'm Googling it. His all-time... Oh, there was like an article about how he might overtake... Oh, he did overtake Steve Nash. It's 90.45. Damn. So Stephen Nash... Oh, what the hell? Why is it not letting me click? Stephen Nash has a free throw rate of 90.43. Curry has a free throw percentage of 90.45. Wow, he actually overtook him. So if you go there and you change it, you get slightly different numbers, but it's basically the same. Like, he usually makes it on the first shot. Okay. So is everyone understanding that the numbers that it gives you are the number of failures until a success? So usually people look at this 0 and they're like, what do you mean he made it after 0 shots? There were 0 failures, which means it only took a total number of 1 trials, and the first trial was a success. Okay, so I'm just going to pause to see if that makes sense to people. Yeah. That's exactly why we're doing this. Where'd my screen go? I keep on like clicking away to like look at different things. So let me put plain text. There we go. So notice that the numbers on the bottom of the bar chart are X's, which are the number of failures before the first success. So if X equals 0, that means there were 0 failures before the first success, i.e. the total number of trials was 1 and you made it on the first one. Right, so you always need to add 1 to this to see how many actual shots were taken. That's what I was talking about, like the 0 right here at the bottom of that big bar. That throws people off because people will say, what do you mean he took 0 shots? That is not the number of shots, that's the number of failures before success. Okay. So, what we're going to do with this now is use this to calculate probabilities. So, let's go back to Shaq. So, suppose that you're wondering what the probability is that Shaq makes it on the first or second try. So you always have to operate with x. So if we're talking about the first try, how many failures? What's x going to be if you make it on the first try? Remember, x is the number of failures. So if you make it on the first try, what was x equal to? X equals 0. So that's making it on the first try. What does it mean to make it on the second try? X is 1. Okay, so what you can do, oops, I keep on clicking the wrong dang thing. We're going to calculate the probability. And what should the name of our variable be? Because we're having Shaq take free throws. What do you want to call the variable? We can call it whatever we want. Free throw, cool. Actually, we should call it failures. Okay, so we are interested in Shaq making 0 or 1 failures. So the number of failures is less than or equal to 1. And failures is distributed according to a geometric distribution where p equals 0.527. So this is going to figure out, hey, what's the chance that Shaq makes it on the first or the second try? And apparently there's a 77% chance of that. Which should make actually. One second, I need to check to see if I type this in the right way because I don't want to say something wrong. One moment. Okay, wait. I think I'm doing something wrong. Just pause for a moment. I'm sorry. I don't want to say it wrong and then realize afterwards that I said it wrong. So I'm like, does that make sense? I'm having this moment where I feel like I'm doing something wrong and I'm not quite sure. Alright, cool. Okay, that would be making it on the first shot. 52% chance. Oh yeah, okay, cool. This worked, yeah. Okay, I guess what I really want to point out here is that this is really confusing. We're talking about making it on the first or second try. So does it make sense that most people would want to put a 2 right here? Failures less than 2? Because you want to say like, hey, what's the chance that he makes it on the second try or earlier? But you don't deal with the actual number of tries. You need to talk about the number of failures, right? So if you make it on the second try, that means that you have 1 failure or less. So let me write that down. So it's common to want to put failures less than or equal to 2, but that doesn't work since making it on the second try would mean making 1 failure. So if we want to talk about making it on the second shot or earlier, that's the same as having 1 or fewer failures, hence failures less than or equal to 1. Okay, so like this is like the trippy thing about this, and even whenever I use it, like I always have to take a moment to think about it and say like, oh yeah, I'm not talking about the total number of trials. I'm doing this in terms of the failures. So if I want to talk about, oh, he makes it in 3 shots or less, 3 shots or less means 2 failures or less. If I want to talk about the fact that he makes it on the second shot or earlier, that means making it with 1 or fewer failures. So what is the chance that he makes it in the first 2 shots? 77%. So there is a 77.6% chance that Shaq makes the free throw on the second shot or earlier. Alright, let's see how we're doing on time. Oh, we're good on time. There's actually some really interesting applications of this, which we're going to look at. Okay. Let's talk about this for taking a test. So let's say that you historically, or how about this? Let's say that you take 25 different tests and only pass, let me come up with a number. Say out of the 25 you passed, what's that number? Too low, too high. Ooh, okay. Let's do 15. So let's say you take 25 tests and only pass 15 of them. Okay, so as of right now, what is the probability that you pass a test given the historical information? So your P in this case is you passed 15 of the 25 tests. Does it make sense that right now your pass rate is 60%? That's what Wolfram is telling us. So, your historical pass rate is 60%. Okay, why does it keep doing that? I keep on trying to click the plain text thing, but it won't let me. There we go. So historical pass rate is 0.6, which is P equals 60%. Okay. Now let's say you're wondering, what is the probability that I need to take a test 3 times or more before I pass. Okay, so are you going to use the number 3 in your calculations anywhere? So like, would you write, my question is, would you write probability, let's just put test for number of tests, like greater than or equal to 3? Yay or nay? And why did I put the greater than? That's a good question. Let's see if this is making sense or not to people. Like, why did I say test greater than or equal to 3? Like, why did I choose to put the greater than there? Any clues? Exactly. Yeah, I'm talking about 3 times or more before I pass. Now, so that's why you have the greater than there, but why am I not supposed to have the 3 here? So there's something wrong with it. So if you pass the test on the 3rd try, well, it has nothing to do with being the greater than is fine, but if you pass the test on the 3rd try, do I actually care about the fact that I passed it on the 3rd try is my question. What do I actually care about? Yeah, so you need to rewrite this as, what was the number of failures? So if I pass on the 3rd try, what is x equal to? 2. So really what this is saying is that I'll have at least 2 failures. So I'll have 2 failures and then a pass. Or I'll have 3 failures and then a pass, and so on. Okay, then you need to go in there and write test distributed according to a geometric distribution. And for my geometric distribution, what's my pass rate? 60%. So if you pass tests 60% of the time, what is the probability that like you need to take some test 3 times or more before you finally pass it? About 16%. Okay, so the chances are pretty low that you would have to like repeat the test 3 or more times before you finally passed. Okay, same thing. I wanted to type the plain text. So there is a 16% chance that you need to take the test at least 3 times before you pass. In other words, there is a 84% chance that you pass on the 2nd or earlier attempt. So my question is, does it make sense how I entered this command here, but more importantly, why I have the 2 as opposed to the 3? That's like a very common mistake. Like people see the 3, oh, we're passing on the 3rd try, or later, we'll put greater than or equal to 3. You have to remember to rewrite, like redo the numbers in terms of the number of failures. Yeah, 0 counts as 1 is the way you should think of it. Because like if you put 0, you're passing on the 1st try, right? So you always subtract 1 from the number usually. Okay, I think we're going to end here in terms of material. So I'm going to